Welcome to the 12th week, that is the last week lectures and of this course, Thermodynamics and Kinetics of Materials. And this is Shashwata. And so, in the last week, in the concluding week, we look at, so we have so far looked at equilibrium, right? Phase equilibrium. So, we have looked at phase equilibrium, we have looked at phase diagrams, we have looked at binary phase diagrams. We did not look at the ternary phase diagrams, but in ternary phase diagrams, it is basically, as you know, we use isothermal section, and if required later, if you want some pointers to ternary phase diagrams, please contact me. So, I will be ready to help you. So, we looked at phase equilibrium conditions. We looked at unary systems, we looked at multi-phase, multi-component systems. We looked at the fundamentals of thermodynamics principles, how they apply to phase change, how they apply to solutions and different solution models. However, we had to look at, we always talked about extremization of entropy as one of the criteria, and then we looked at all this for simple systems. We looked at arrived at the different thermodynamic conditions. For example, P alpha equals to P beta. If alpha and beta are in equilibrium, you have P alpha equal to P beta equal to P gamma. Say alpha, beta, gamma are in equilibrium. Then we looked at also for each constituent. Say you have two constituents, mu a alpha equals to mu a beta equals to mu a gamma. So this is another equilibrium condition. Similarly, for the other component, if I have a binary system, mu b alpha equals to mu b beta equals to mu b gamma. We also looked at the thermal equilibrium, T alpha, T beta, T. However, we need to discuss about stability, right? Stability, which is related to the second derivative, right? Stable equilibrium. Whether the equilibrium is a stable equilibrium, it's a metastable equilibrium. We have discussed metastability, but we have discussed even unstable systems, right? We have discussed instability gap below at a temperature below which a solution becomes unstable and phase separates. We have looked at that, but how we formally treat stability is something that we will discuss. And in stability, in the context of stability, we look at some aspect like numerical modeling. So, if numerical modeling means we basically will use numerical model, and then we can use something called from the GX curves, that is from the solution models. From the GX curves, you will see some GX curves, and from that, if we can use common tangent construction, so basically that is something that we will do, right? GX curves and common tangent construction. And also we look at thermodynamics of reacting systems. We initially at the initial stages we discussed from the thermochemistry, thermodynamics of reactions in terms of reactions, whether they are endothermic or exothermic. But here we will go a little bit more detail. We will look at Illingham diagrams as example, and finally, we will look at some examples of interfacial thermodynamics. So these are the three lectures are there. So over the interfacial thermodynamics and a brief introduction to irreversible thermodynamics, which is basically the basis of kinetics, and there we will look at particularly how it applies to this flux force relations, right? And this is where we will conclude. Although the irreversible thermodynamics part, if you want further information, because it's just an introduction, a very preliminary introduction. So if you want to go further deep into the irreversible thermodynamics part, as you can see in the layout of the course, we initially had a lot more on diffusion. However, we changed the layout a little bit because you see there is we discussed all the thermodynamic principles in details. Okay, so we basically did not want to get into a lot of kinetics, but we wanted to get into the idea behind kinetics, the principles of kinetics, and that is what I will talk about, and that is where irreversible dynamics comes about. However, as you can see that these are very involved and detailed, and it may require a separate set of lectures, right? And we can also have discussion offline. So as you know, you can reach me at my email ID, and if you have any doubt, and also there is a forum right now. But in the forum, mostly what is discussed in the class is what will be discussed further. But beyond the forum, if you want to know something more advanced, you can always contact me by over my email and send me an email, and I will try to help you as much as possible. Now I'll start with the criteria for stability. Now you know, when we talk about stability, one of the easiest ways to understand stability is by using a mechanical analog. So if I take a mechanical analog, think of a piece of material which is in the form of this box, as you can see here. So this is like a rectangular parallelepiped. So if you look at this, it's not a bar. It is like, in cross sectionally, you think of this is like a book. You see, so and you are looking at a book. So basically, you are looking at something like this, and then you have this and this, right? So you are looking at that. Now, if you look at this squarish bar or bin, or if you can call it this material, you can immediately see here there is a long edge and there is a short edge of this material, right? You are looking at the cross section here. You are looking at the cross section here, but if you can think of it is like a column, a small column, rectangular column like this. Think of a rectangular column. If you have played a game of Jenga, you will see in the Jenga there are these pieces, these wooden pieces. You think of these three-dimensional wooden pieces or blocks. So I am talking about one block which has a long edge and which has a short edge, right? Which has some thickness and which is also having some height and some width. Okay, so I am not looking at the width as such, but we are looking at the thickness section and the height. Now, if you see the long edge, if the long edge rests and my center of mass is somewhere here, see, at the lowest level, where the long edge is resting on the ground or on the surface. So this is your surface. This guy is your surface on which the long edge is resting. Now, if the long edge is resting, if you look at this orientation, here is your center of mass. Roughly, here is your center of mass. Right? This is the weight of the block. Now, however, you can also set the block in such a way that it is resting on the short edge instead of the long edge. Instead of the long edge, it is resting it is resting on the short edge. Now, in this case, for example, even if I move, if I try to force it, if I try to apply some force on it, it will move here and there slightly, but it will not destabilize, right? It will not destabilize. It's a stable equilibrium, right? It will just remain as it is. However, if you look at this, the metastable, if you see, you can immediately understand why it is metastable, because as you can see, the center of mass has gone up, right? The way I have listed it on the short edge, the center of mass is somewhere here, and if you push it slightly, then, right, not very slightly, but yeah, you give a little shove, then basically if you give a little shove, then it falls, right? It falls such that it again, so if I say, for example, produce a force like this, it will fall, and once it falls, it will rest on this stable equilibrium. So if you see, stable is the lowest, if you look at the stable equilibrium, this is the lowest energy state. Now, if I push it or shove it a little bit, then it will fall in such a way that it comes to a more stable equilibrium. So the metastable equilibrium, so that is why this is called metastable, because from metastable I can go to further more stable equilibrium. Now, if I look at unstable, say there is something called unstable equilibrium. This unstable equilibrium is something like I am balancing it on one corner. Somehow I know, or somehow I'm like a magician, I have balanced it on some corner, and it's just barely there. So you can see a small touch, a small touch or small disturbance, even a small sound, it can immediately, if you will see that it will immediately fall on the long edge, right? It will fall on the long edge. It will again, the unstable one will tend to go. So there are two things that can happen. This unstable one can fall like this, and then it will rest on the long edge. It becomes a stable equilibrium. So this guy, if it falls like this, however, there is also a possibility that I force it like this. Then it will just go up, and it is possible that it will come to a metastable equilibrium. So the unstable one can either be metastable or be stable, right? The unstable one can either be metastable, can either reach a metastable equilibrium if I basically force it this way. If I force it this way, if I just touch it this way, immediately it will fall to the stable equilibrium, right? So stable equilibrium is the one that it does not want to change at all, unless we have vigorously disturbed it, unless we have moved it from there and we have forced it to be metastable or unstable. It will remain in stable equilibrium forever. However, when it is in metastable equilibrium, if there is an energy or a driving force, metastable equilibrium will change to stable equilibrium. Correct? Metastable equilibrium will change to stable equilibrium. Now, if I look at this from an energy point of view, if I look at this from some energy point of view, then if E is the energy, then think of this. You are somewhere here. Now here, I'll call it locally stable equilibrium. But if I mean here, for example, the ball will roll either this way or this way, right? I have a ball here. If you can see, there is a ball here. And the ball can either roll this way, right? You have a heel here, you have put a ball here, and this is the energy. So this has the highest energy. As you can see, this is the energy landscape, right? This is the energy landscape that I am talking about. And say this is my position coordinate r. Okay, position coordinate r. So if I have such a coordinate, and if I have some particle here resting, the particle here will be in a highly unstable state. A little push can either push it down this hillside, or along this hillside. Now if you see, the driving force for going here is much more than the driving force for going here. However, if it starts rolling this direction, if it starts rolling in this direction, it will reach metastable equilibrium rather than the stable equilibrium. Correct? It will reach metastable equilibrium. In fact, I can think of a better diagram. Say, for example, I have this. Now you see, I have a ball here. Okay, so let me just this. Now, if the ball is rolling, this part is becoming a neutral equilibrium, so that is where I want to change it a little bit to a stable equilibrium. So basically, make it little unstable. Now you are here, somewhere the ball is somewhere here. Okay. Now you have just given a little displacement, means you have displaced it a little from the position. So you have given a little displacement from this position. What happens? It falls in and it goes here. Right? The ball has gone here. Right? It is going here. However, if I force it a little more, if I give it a more than a slight push, if I make it a larger push, then it is possible that the ball will basically directly follow this trajectory and come. Now, as you can see, this is the stable equilibrium. This is the metastable equilibrium. And this is the unstable portion. Right? So you have stable, metastable and unstable. So as you can see here, so if I want to apply this mechanical analog or this energy surface, how do I basically understand it in terms of phase stability? In terms of phase stability is what we will discuss now, right? So we have given a mechanical analog. See, look at this. You have given a mechanical analog of phase stability, and you have also given energy surface. You have drawn some imaginary energy surface. We look at the energy surfaces we generally encounter, and this is energy surface is a function of position, right, on the energy surface. So if you see, there are positions where the equilibrium will be unstable, there are positions where the equilibrium will be metastable, and there are positions where the equilibrium will be the most stable one, and once you have gone to the metastable, to the unstable one, you do not, to the stable one, the most stable one, once you have gone here, you don't want to, there is no way, unless there is a big external force, you cannot go to the unstable one or the metastable, right? However, a very little disturbance to the unstable equilibrium will lead it to either a metastable equilibrium, or it may lead it to the more stable, most stable equilibrium, right? So this is what we are talking about, and here is an example here, and I am talking about another interesting case here. So you have a very flat surface, and the particle is here, and you have very flat surface. Now this has same energy, this has same energy. So if I am here, same energy. If I am here, in all these points along this surface, the energy remains the same. So this is called a neutral equilibrium, right? You just remain there. If you displace it slightly, the energy does not change. So it's called a neutral equilibrium. Now look at metastable equilibrium. Why am I calling this metastable? Because there is a possibility that there is a farther downward slope somewhere. So you have, say for example, some more downward slope here, right? So it is possible, right? So that is why we call it a metastable equilibrium, right? We call it a metastable equilibrium. You can also call it stable equilibrium if there is no such metastability. If this is the lowest energy position, if this is the lowest energy position of the ball, then this metastable equilibrium becomes a stable equilibrium, right? Metastable, it becomes a stable equilibrium. However, have a look at the instability. Say, have a look at this position where you are at the top of the hill, the peak, and if you are at the peak of this energy barrier, so if you are in the peak, this peak is basically the giving you the unstable equilibrium condition. The unstable, because if I displace it this way or this way, the ball will just roll, right? I displace it very slightly, the ball starts rolling. A little disturbance, it will just go to either a metastable equilibrium or a stable equilibrium, right? So that is the idea. Let us look at that in the context of this solution model, right? We have already looked at something called phase separation, right? We have looked at the regular solution model where we looked at something like phase separation, where A atoms favor A atoms and the B atoms favor B, right? So basically, if I want to write the excess energy due to mixing or the energy due to mixing, then it has one delta S mix, right? It has a delta S mix. This is your delta S mix contribution, and there is a T delta S mix, right? So minus T delta S mix basically gives you RT XA ln XA plus XB ln XB for a binary solution. If I take a binary solution, this term is basically minus T delta S mix, right? Delta S mix. And then you have the regular solution parameter. So this is the delta H mix. Right? XA and XB are the mole fractions of N. In fact, if since XA plus XB is 1, I can take 1 minus X and X. So basically this becomes RT 1 minus X ln 1 minus X plus X ln X. This is the same term here. And then this guy becomes omega X 1 minus X. Just writing it this way, right? Now, I want to basically take a derivative of it. So dgm dx basically comes out to be RT ln X by 1 minus X plus omega 1 minus 2X. Okay. So basically, this basically gives me a slope, right, of the curve, the slope of the curve at any point, right? It basically gives me a slope of the curve at any point. So if I have a curve like this, one single curve. So if I have a curve like this, right, and then basically this is my So if I have this curve, for example, as a function of x, so if I look at this as x, x is the composition of, it's a mole fraction of b, say, and this is my the y-axis. Y-axis is say gm. Now this is gm mix, for example, the energy of mixing. Now I take any point here. I take any point here, and then I draw a slope, and the slope is basically given by this relation, right? This slope is given by that. So this is the slope of the curve. So I can take this point here. I can take the same point somewhere, say here. I can take this. I can just take a slope. If I want a slope like component tangent, then this is the tangent. This is how the, so basically this is the first derivative is the slope of the tangent drawn at some composition x. This is the slope of the tangent drawn at some composition x or xp. Okay, so that is the first derivative. And see the first derivative if you can understand this. So basically, if you can have a look at this, but you see, so this is exactly what I wanted to tell. There are some points where the slope becomes 0. See, there is one point where the slope becomes 0. There is another point here where the slope becomes 0. Right? You can notice that point. So this is one point where slope is 0. This is another point. This is another point. So basically, if I draw 3 tangents like this, and this is another point where slope is 0. Right? There are 3 points on this curve where slope is 0. Now let us have a look. There is something other than slope that is changing here, right? And we will try to look at that. Okay. So basically, what I told, you have dgm mix, right, which is RT. So which is RT ln x minus ln 1 minus x plus omega 1 minus 2x. Remember, when you plot this curve, when x equal to 0, ln 0 is undefined. When x equal to 1, ln 0 is again undefined. So as a result, when you plot this first derivative, right, you can plot the first derivative, you can plot the free energy, and if you plot these things, remember to use an axis where the limits are between 0 and 1, but not exactly 0 and 1, because at 0 and 1, the logarithm terms are undefined. Now, have a look at the second derivative. Now, you have the first derivative, so you can go further and you can do the second derivative. So, you have RT remains, and you have ln x becomes 1 by x, and this becomes plus 1 minus 1 by 1 minus x. Why? Because you have a 1 minus x, and here you have minus sign. So ln 1 minus x, if you take differentiation, so it becomes 1 by 1 minus x with the minus sign outside. So, but there is already a minus sign, so minus minus becomes plus. So you have a plus sign. You have a plus sign. Note that there is a plus sign. Right? So this one has a plus sign here, and then you have the third derivative. I go further, I take the third derivative, then you have RT. So if you look at that, you have RT and then 1 minus x whole square, right? 1 minus x whole square, right? Right? 2 omega, omega is a constant, right? So this goes to 0. Now you have 1 by x square, so minus 1 by x square. See, minus 1 by x square. But here it is minus 1 by, so this is 1 minus x whole square. So minus of 1 minus x whole square, but there is also minus x here. So this becomes plus. So plus 1 minus x whole square minus 1 by x square into RT. Now if you look at the third derivative and basically put x equal to 0.5, now you see you have 1 by 1 minus 0.5, which is 0.5, 1 by 0.5 whole square minus 1 by 0.5 whole square. So at x equal to 0.5, this guy basically becomes 0. Now this guy, if you see, if you have d2, so basically if you have d2g dx square d2 gm dx square as some quantity, say, let us call it some quantity, say y. Now, if that is so, d3, this is basically d3 gm dx cube, which is nothing but dy dx, right? So basically, this is the slope of the second derivative, right? It's a slope of the curve that is of the second derivative, right? So basically, now if you look at this, so you have gmx. Say for example, you have gmx here. So you have gmx here. You have one point where the dgm mix dx equal to 0. This is one point where it is, and this is another point where dgm mix dx equal to 0. And these points are basically where the tangent line becomes parallel to the x-axis. Tangent line is parallel to the x-axis. The slope is basically 0. But when you look at the d3 gm dx cube equal to 0, then you get a value of x equal to 0.5. What does that really mean? Okay, so basically you have a curve and you have its slope, and the second derivative basically represents its curvature. Second derivative represents its curvature. Now, if you look at the curvature, the second derivative, so in this case, the curvature is negative, right? In this case, if you see this is curvature is negative, and this is where curvature is positive. Now, if you see, you have a negative curvature here, you have a positive curvature here, and the curvature is changing, right? So here, so you are looking at this point where you are in the maximum, so you have a negative curvature here. Negative curvature means the second derivative is negative, means the function is the extremum of the function is if I have a function fx, if I have a function f of x, if I tell f prime x equal to 0, and I get x equals to xe. Now I do f double prime x. Now at x equal to xe, I get less than 0. That means xe is at xe the function is a maximum, right? The function is a maximum if the second derivative is negative. Now if the curvature is, that means the second derivative is negative, means here what we are talking about, here the second derivative is indeed negative, right? The curvature indeed is negative. Here the curvature is positive, right? It has a positive curvature. Positive curvature means it's a minimum, right? When f double prime x at x equal to xe is greater than 0, that means xe is where the function has a minimum, right? So this is the idea, right? So we are just looking at the same idea. So basically what we are telling is, okay, you have calculated the function, you know the function, for example energy, or say free energy, you know the function. Now you take the first derivative and equate it to 0. What do you get? You get the extremum values. Now you want to check whether the extremum values indicate a maximum or a minimum. If it is a maximum, as you can see, if you remember the ball rolling example, then if the ball is here, then obviously this is basically an unstable equilibrium. However, if it's a minimum, it has nowhere to go, right? It is already in the minimum energy level. It wants to remain there. If you can see the second derivative now will be positive. So positive indicates minimum, negative indicates maximum. We can immediately see that, right? So this is basically the maximum. This is maximum. And this guy tells you minimum. So you have positive curvature here, you have positive curvature. So basically what you have here is positive curvature. That means the second derivative is greater than 0 at the extremum value, right? The extremum value is where the slope is basically 0. The extremum value you calculate by making the slope 0, and then at the extremum value, if you calculate the curvature is positive. That means it is a positive curvature, means it's a minimum, okay, of the curve. It's a minimum of the curve. Now, if you again, slope is 0 here also, right? Slope is 0 here also. This is an extremum value. So as you can see, this is the extremum value. Now at this extremum, the second derivative is less than 0. Second derivative is less than 0 means this extremum is nothing but a maximum, right? In this case, this extremum that you have, this extremum is nothing but a minimum, right? So now if you look at this term, so there is also a possibility that the second derivative is 0. Now second derivative is 0 basically gives you the point of inflection. Okay, this is called the point of inflection. Inflection is where from positive curvature you are changing to negative curvature. So basically you are changing from positive curvature to negative curvature through zero curvature. This zero curvature, so these are zero curvature points, and these points are called points of inflection. The points where the curvature becomes 0, so zero curvature are the points of inflection. By the way, the zero curvature points indicate something called as spinodal decomposition. Spinodal decomposition is where you have a oil-water mixture which is homogeneous. Now you are taking it below at some temperature which is below the spinodal. It spontaneously phase separates without any driving force. Okay, so this inflection points. But what I want to tell you, what I want to emphasize is that there is this. So if you have this type of double well potential, double well means it has two wells, right? It has two wells, one well here and one well here, right? And this energy I am drawing now as a function of composition. Tomorrow I can draw it as a function of some order parameter. Okay, so now if you see that it has one minimum here, but there is one maximum, right? So there is one maximum. Now if it is maximum, then it has negative curvature. This is positive curvature. This is again positive curvature. So from positive to negative, if I have to travel, I have to go through 0. Now zero curvature is where basically it indicates the locus of the points for which any energy, any fluctuation. So if I have a ball here, any small fluctuation will reduce the energy. See, here the energy was. Now the energy is now, if you see the energies, so if it reduces, if I come here, then the energy has reduced, right? The energy has reduced because I have this thing and this thing. So average, say, I can think of this energy. Now if you look at that, I go further down and my energy decreases. So my energy decreases until I finally reach the common tangent, right? Common tangent basically gives me the equilibrium states, the two equilibrium states that I reach. That is the double well, this well and this well, right? So this is right. Now, if you use a regular solution model and you want to basically write d2gm mix dx square equal to 0, then what you get is RT 1 by x by 1 plus 1 minus x minus 2 omega equal to 0. Now, if you remember, so now if I do further simplification, so I get 1 by x plus 1 by 1 minus x equals to 2 omega by RT, right? This is the further simplification. So further, if I do, because x times 1 minus x is there, so if I just make it inverse, so then what happens? RT by 2 omega equals to x times 1 minus x, because x plus 1 minus x equal to 1, right? So now you have RT by 2 omega equals to x times 1 minus x, right? Now when x equal to 0.5, your RT by 2 omega becomes x times 1 minus x, where x equals 0.5 and 1 minus x is 0.5. So RT by 2 omega equals to 0.2, or 2 omega by RT equal to 4. Right? If I do the inverse, if it is 0.25, then 2 omega by RT has to be equal to 4, or omega by RT has to be equal to 2. So now this value at 0.5, right, at 0.5 gives the, so first we have to understand why 0.5. Why did I look at 0.5? Because if I basically use 0.5 in this equation, so what I get, ln half minus ln half, which is basically 0. So this term becomes 0, and this one 1 minus 1, right, 1 minus 2x, so this also becomes 0. So this is 0 and this is 0 at x equal to 0.5. Now at x equal to half, the second derivative, let us look at x equal to half, the second derivative. What happens to the second derivative at x equal to half? It is basically, if I look at the second derivative at x equal to half, what is the second derivative? This is the second derivative, right? So second derivative at x equal to 0.5 is basically RT 1 by x is 2, 1 by 0.5 is 2, and this is 2. So 4 RT minus 2 omega. Now this has become 4 RT, right? 4 RT at minus 2 omega at x equal to 1 by 2, right? 1 by 2, yeah. So it becomes 4 RT minus 2 omega at x equal to 1 by 2. Now 4 RT minus 2 omega, if it is negative, then only 4 RT minus 2 omega, if it is negative, that means if 4 RT minus 2 omega has to be less than 0, then basically 2 omega has to be, 4 RT has to be less than 2 omega, or 2 omega has to be greater than 4 RT, or omega has to be greater than 2 RT. So if omega is greater than 2 RT, then basically you will start seeing that 4 RT minus 2 omega is negative. That means it's a maximum, right? It's a maximum. So the maximum, now it at exactly x equal to half, it's a maximum. Now at exactly x equal to half, if I want to find, if I want to go to d2gm dx square equal to 0, which is the inflection point, I basically get a very important quantity called the critical temperature, which is Tc equals to omega by 2r, right? We have got Tc equals to, comes out to be, so RT by 2 omega equal to x into 1 minus x. Now I put x equal to half, so then it becomes half into 1 minus half, which is half into half, which is 1/4, right? It becomes 1/4. So RT by 2 omega equal to 1/4, right? Or 2 omega by RT equal to 4, or omega by RT equal to 2, and Tc equal to omega by 2, right? This is the critical temperature. So if you look at a Michelin gap phase diagram, with the Michelin gap, if you look at a phase diagram with the Michelin gap, this is my G and this is my X, and yeah, I'm approximating it. Okay, it is. So if you see this C0, sorry, this is not G, this is basically the phase diagram. So this is T and this is X, and this point is TC. Now above TC you have alpha, below TC you have alpha 1 plus alpha, right? Above TC you have alpha, and below TC you have alpha 1 plus alpha. Now if I take these are the two phases, or I can call this like I have one homogeneous mixture beta, and this is beta 1 plus beta. Now if I tell alpha equals to omega by RT, okay, so that's why I did not want to use alpha, because I have used alpha for denoting this parameter, right? So this beta is basically a phase, right? Beta is a homogeneous solid solution, and say this is A and this is B of A and B. Now below Tc, once I go below Tc, what I see is that beta decomposes into two phases, beta 1 and beta 2, right? Beta 1 and beta 2. Okay, so there are, so if when you learn about phase transformations, you will see that there are two ways for beta 1 and beta 2 to form. In one case, you have beta 1 matrix in which there is beta 2 nucleation. In another case, the beta, for example, if the composition of beta is 0.5, then you will see that below the critical temperature, beta will spontaneously decompose without any push, without any driving. So it will spontaneous, because why spontaneous? Because if you look at the free energy composition diagram, this is what. So you are here. So again, as I told you, you are here. Now if you go a little bit here or here, your energy has decreased, right? Your energy was here. Now the energy has come here, or energy has come somewhere. So energy is basically continuously decreasing. Okay, if I basically if I start falling like this way or and this way, right? So this is exactly what is the root cause of this spontaneous phase separation. So if you are within the negative curvature region, Even a small fluctuation will lead to reduction in free energy. As a result, there will be spontaneous phase separation of the solution into two phases, right? One is A-rich phase and another is B-rich phase. And as you can see here, the diffusion is not, so previous diffusion is down the chemical potential gradient, but it is not down the composition gradient, right? It is not down the composition gradient, because if you see, A becomes richer in A and B becomes richer in B, right? So this is something that you can look at. So if you see, if alpha equals to omega by RT, and if you see that omega by RT equals to 2 is the critical value. Omega by RT equal to 2 is the critical value. And from there you can write T equal to Tc when Tc equals to omega by 2R, right? 2 you take this way, T you take this way, so you get Tc equals to omega by 2R. But you see omega by RT is the critical value. Now if, as I told you, if omega greater than RT, alpha C is the critical value. So basically, if I tell omega by RT greater than 2, or as I told you, omega greater than 2 RT, then basically what you get is phase separation, right? You get is phase separation. If alpha is greater than alpha C equal to 2, so omega by RT equal to 2 is the critical point. So if alpha is greater than alpha C, what you basically get is phase separation. If alpha equal to alpha C, you get critical, right? That's the critical point. So this basically gives you a critical point. And if alpha less than alpha C, right? If alpha is less than alpha C, what does this mean? Omega by RT less than 2, right? So basically, if you see, that means omega minus 2 RT is less than 0. So in this case, you basically get a homogeneous single phase. This comes again from this, right? This is no longer, if omega minus 2 RT is less than 0, then basically 2 RT minus omega is basically positive, right? 2 RT minus omega is basically positive. If you remember, when I put this expression, the second derivative, it becomes 4 RT minus 2 omega. 4 RT minus 2 omega. Now 4 RT minus 2 omega is basically the same as 2 common you take, so it becomes 2 RT minus omega. Now if 2 RT minus omega is positive, then the curvature is positive. Curvature is positive means it indicates that it's a minimum value. If 2 RT minus omega is negative, then only 2 RT minus omega is negative means omega is greater than 2 RT. Omega is greater than 2 RT means omega by RT is greater than 2, or alpha is greater than alpha C. Now if alpha is greater than alpha C, basically what you will see is phase separation. Alpha equal to alpha C, you basically see a critical point. Critical point is where the beta phase coexists with the beta 1 and beta 2, so it's critical phenomenon, and critical phenomenon is somewhere your free energy looks a bit like a neutral equilibrium, so basically it becomes a bit degenerate, and what you basically see is something like this. So if I draw, so it becomes much flatter, right? The energies become much flatter, right? As you are approaching the Tc, the energies start becoming flat. So at one point at T equal to Tc, you have some sort of a neutral equilibrium. Any state is possible, right? You cannot really apply the normal way of applying thermodynamics. So you use something called, there is a branch to understand the critical phenomena. Okay, so the understand the critical phenomena, where you use some other more sophisticated statistical mechanical theory to understand that critical phenomena. So at the critical value, basically you are telling that's the critical point where you cannot basically tell what is the state of the system, whether it's a homogeneous state or it's a phase separated state. You cannot really tell, because all of the states have become degenerate, right? So that is the idea. So if you look at that, if alpha, so if I want to plot it, if you see, if alpha is less than alpha C, what you get is a minimum, right? What you get is a minimum. So alpha is less than alpha C, and if you look at that, this is how your free energy, this first derivative looks like. And as you can see, it intersects the x-axis at 0.5, correct, when alpha is less than alpha. And if you see the second derivative looks this way, and the third derivative again looks this way, again with a value at 0.5, right, again with a heat at 0.5, right. This is the at 0 line, right. Now if you look at alpha equal to alpha c, you see again, as I told you, this becomes very flat, and you have this type of a curve where you see it extends, right. It is like, it's not exactly 0.5, it can be here, it can be here, right. So this is like, these are the points, like it varies between 0.21 and 0.79. By the way, this basically defines your negative curvature region, right. This is between these 2 points. It's not exactly 0.1 and 0.79 in this case. So you can basically calculate what will be these values. These 2 endpoints basically tell you the confine of the negative curvature. This is the negative curvature. As you can see here, that you have this curvature value here, where curvature value is 0 here, and then the curvature value increases, right. So basically, if you look at this critical phenomenon, it becomes slightly interesting here. It becomes very flat line here, the curvature becomes flat line, right. If you can see the curvature here, right, if you are seeing GM mix here, so it becomes like this, right. And then you have obviously the alpha greater than alpha c, where you have these inflection points, right, where the second derivative basically goes to 0, and then you have a maximum and you have 2 minima. And if you look at this plot, you have one root here, right. This is x equal, this is basically y equal to 0, or d. So this is the slope, right. The slope of the curve becomes 0. So slope of the curve becomes 0 here, the slope of the curve becomes 0 here, here, and here. So these are the corresponding roots, right. But at these 2 points, you have minima. This point corresponds to this point, this guy corresponds to this point, and this one corresponds to this one, right. So similarly, you have the third derivative here and the second derivative here, right. Now you can also calculate delta mu b. Delta mu b is basically nothing but mu b solution minus mu b solution minus mu b pure, right, mu b pure state. So basically, if you look at delta mu b is basically delta Gb bar mix, right. This is the partial molar Gibbs free energy, but this is the partial molar Gibbs free energy of mixing. So this basically equal to delta Gm mix plus 1 minus xb delta Gm dxb. You can look at the previous partial molar quantities lecture, and you can basically see this is what we have written. And if you calculate, simplify, then you will basically get this guy, because it's a difference between mu b minus mu b 0. This is nothing but equals to RT and AB, where AB is the activity. Now, unlike an ideal solution model where AB equals to XB, here AB will be different, right? And if you look at this the first derivative, again you get 1 minus XB d2 delta G dx square, and this becomes RT dln AB dxB. Now, if you do the second derivative, basically what you get is this RT by AB dAB dxB, or dln AB dxB, basically RT dln AB dxB, and that basically gives you the thermodynamic factor. It will become very useful when you study diffusion, okay. But as you can see here, so this guy, this is basically d delta Gb bar mix. So you have d delta Gb bar mix dxB, delta Gb bar is this. So if you look at that becomes basically d delta Gb bar mix. So basically you have this one and you have this guy, because you have XA and this stuff, right? This is your delta Gm mix. So this becomes d delta Gm mix dxB, but you have also plus d delta Gm mix dxB. So 1 minus xb into d delta Gm mix dxB, but there is 1 minus xb, so minus. So this one minus this one will go to 0, and then you will have the second derivative, so which is basically equal to x. Okay. So basically, as you can see here, you can calculate the partial molar partial molar quantities of mixing, or partial molar potential of, right, partial molar chemical potential for mixing, right, for the element B as well as for the element B. Right now, basically, what I want to say is that there are, as you know already, and I don't want to again discuss, because I have already discussed the standard states. Okay, so if you look at that, if you always have the standard states, you can use any standard state as whatever possible. However, this is something that I wanted to tell you, because when you look at regular solution models, instead of XB, right, in most of the cases we have been using ideal solution models so far, but you can also use regular solution models like this. But you have this like mu BS equals to mu BL, because this is your solid, this is your solid free energy, right? This is your solid free energy, and this is your liquid free energy, right? And if you have that, so you are seeing that this guy minus this guy, now this has to be equal to this, but you have this part and this part. So basically this equal to this minus this equal to 0. So this becomes RTLN AB by AB solid by AB liquid, right? AB solid by AB liquid is basically, if you take the other way, so this becomes liquid minus solid, right? This is a pure B liquid to solid. So this is solid to liquid transfer. So this is solid to liquid transformation or melting, right? So this is the transformation. Now this is basically again comes as a ratio of the activities, right, in the solid state and the liquid state. Now if you look at that, so only thing that I want to tell, that you can use solid as a standard state or a liquid as a standard state, does not really matter. The tangent construction does not change. The tangent construction does not change. The common tangent construction does not change. That means the equilibrium values do not change. Whether I am using this one or this one, that really does not matter. As long as I am consistent that I am taking B liquid as the pure as the standard state, and A also I am taking the liquid as standard state, or for A I can take the solid as standard state, well that for B I can take the liquid as standard state, or vice versa. But whatever I take, the tangent construction, which basically gives me the equilibrium compositions and all, that do not change, correct? That do not change. And if you see the activities, if you look at activities, and if you think that activity is the same, is based on mole fraction, as you can see, this activity and mole fraction, you have a slope here. But as soon as you go to the two-phase region, right, this two-phase region EF, between E and F, here you basically see there is no changing activity. Again, the activity changes in the as soon as you receive the as soon as you cross F, right, you are in the solid state, right? So basically it becomes like. Now if you take liquid as standard state, what happens? You go liquid is standard state. So basically again you are reaching E, and then you have EF, where you have the activity constant, and then from F you are going to the solid state, right? From F you are going to the solid state. So it does not really matter. Only thing that matters is, so EF, nothing changes. Only thing that matters is the activity. If I do it with respect to the solid as standard state, the activity goes to 1, right? Because the solid is the most stable state in the standard, most stable standard state. So that's why the activity goes to 1. But here, if I take liquid as standard state, then the activity is not equal to the same as XB. But if I take solid as standard state, it becomes exactly equal to. Now I'll just show you. So all these things I can basically model. So I'll try to find quickly tell you how to model this. So if you just open terminal, I'll just open terminal and show you how do I model this stuff. So basically I'll open a terminal here. Here I'll open something called, so I'll use a little bit of Python here. So don't, I will share these notebooks with you. I have 2 notebooks here that I have written. Share them. So last modifier. Let's look at the phase separation first. So as I told you, I haven't taken 0 and 1 as I told you. I have taken an array between 0.00001 and 0.999999. I have avoided 0 and 1 because log is undefined at 0 and 1, right? And then I am taking a R value of 8.314 and the omega value that I have taken is 16,000. I have taken 16,000 as omega value, 16,000 joules, right, as omega value, joules per mole, right, and you have R is 8.314 and I am taking a temperature range between 400 and 1400 with steps of 100, okay, and I will show you how as you increase as you go to higher temperature and as you go to lower temperature. So as you are at the lower temperature, you will basically see this double bell type of curves, but as you go to higher and higher temperatures, basically entropy starts dominating and you will basically get into a homogeneous solid solution or a homogeneous. So as you go to a higher temperatures, you can go either to a homogeneous solid solution or to a homogeneous liquid solution, and I will just show that what happens. So if I just restart and clear out all output, I have already written it, I have tested it, so I'll just show you. So this is basically a plot which will show. So if I run this, so you basically see that at 400, for example, 400 is this one, 500 is this orange curve, then 600 is this one. So as you can see that you have these positive values of when it is free energy of mixing only at lower temperatures, right? There you have the positive values and you have basically this inflection points, and you can see that these energy curves are cutting the x-axis and all, and so it becomes positive. However, as you go to 700, 800, 900 and so on, you start seeing that it is becoming. So if around 700 you still see a double bell, at around 800 also, or around 900, but as you go to something like 1100, 1000 or so, you basically see that it has become a single homogeneous phase. But here you can see that if you can look at the arrow, then I will basically go into one of these compositions, like this composition as well as this composition. Now I can actually find out what are these compositions, what are basically these compositions. So for example, I use SciPy library and I solve for this. So I am solving basically since this is a single free energy and I am looking at the minima, so I can directly calculate the minima. Minima calculation means I am taking the first derivative, right? This is the first derivative, and I am setting it to 0, okay, and I am setting it to 0. So first derivative of the free energy of mixing, and if you can see the first derivative, you can see how it cuts the x-axis. X-axis also is something I have drawn. So if I look at that, you can see here. So at 400, for example, you are here. So this is where you are cutting the x-axis. Now at 500, you are somewhere here in between, right? And 600, you are somewhere here, this green line. So it is hitting the x-axis at this position, which is close to 0.1 or so, right? And this is this position, this green curve, which is close to 0.9 above, slightly 0.9 above. So basically, as you can see, as you go to temperatures around say 1300, 1200, 1100, 1000 and so on, you start seeing that basically it is passing only through a point of 0.5, correct or not? You are seeing only it is passing through a point 0.5. So that means it is no longer phase separated. As you go to higher and higher temperatures, the phase separation tendency goes down, right? And if you look at that, I have printed something. So I basically printed also. So for different temperatures like T equal to 962 or so, I am printing. Say for example, I can solve this for T equal to say 400. If I look at T equal to 400, then basically I'm just solving it for a given temperature. So you see one of the points is 0.008. So if you see at T equal to 400, you are basically getting this point, which is basically this point corresponds to 0.00877793, and therefore this will be 1 minus 0.00877793, which is like very very close to 0.9. Now I have done it for different temperatures like 400, 500, 600, 700, 800, 900. So you can see here I have done it for different temperatures, right? So I can actually take push here and then I can put it here and then I can do that here and do this, so that you can see all the data. So these are all data points. So you have 400, you have this data point, and then 500, you have this data point. So this is on the CA side, and CB side is basically nothing but 1 minus CA, right? 1 minus 0.008, okay, at 400, 1 minus 0.02 at 500, 1 minus 0.09 or 0.5 at 600, 1 minus 0.09 at 700, and so on, right? So basically, if you see at 963, 1 minus 0.5 is nothing but 0.5. If you go beyond 963, I go anywhere beyond 963, say let us go to something like say 965, you will see that there is only one root, and that root is basically equal to 0.5. So it is returning to a homogeneous solution. So basically, if you look at 965, you see you got 0.5. Now if you go to 964, again it becomes 0.5. So at 963, you see a value which is not equal to 0.5. At 963 also it is 0.5. You just go below 963, like 962, you see that now it is 0.486. So you are very close. You are very close, right? At 0.962 is 0.486. That means the other one is 1 minus 0.486. So if I now plot this, if I now plot all of these, so basically if I do this and then I plot these two, what I get is a phase diagram. See, this is my mesonetic gap, right? So this is around 963 is where, or 962 point something, where you basically get for alpha equal to omega equals to 16,000, you basically get this as the TC. You can basically use omega by 2r to check whether you get the correct TC, right? Omega by 2r, so basically it will give you some value like this, right? So this is basically you can do, and so I have made it slightly smoother here by interpolating. So you can see the same curve. Okay, so basically I did the free energy and looked at the first derivative, and from the first derivative we're cutting the x-axis. X-axis is the y equal to 0 line. See, y equal to 0 line. So this is the y equal to 0 line, and basically you can see that at lower temperatures it cuts at 2 points, right? It cuts at 2 points, and it also cuts at the point here, right? This is the maximum point for the low temperatures. However, at high temperatures, this is the only point, right? This green line or something which is drawn around say 1200 degrees Celsius, or this yellow line that you can see here, they are only one value, right? There is only one maximum value. So basically what you are trying to say is that if it is so, then basically it's a single homogeneous phase. So, right, single homogeneous phase. Say for example, at 1100, if I look at the curve, the 1100 curve is somewhere here, right? This line, this one, and this one is somewhere here. So you can see here it has become such that you have the minimum at 0.5, and basically right, you have a single homogeneous phase, not a maximum. Remember, at 0.5, now 0.5 is your single minimum point, right? See, as you go to lower and lower temperatures, your 0.5 now becomes a maximum, right? And you have some other values at the minimum, right? So this is what we have looked at, phase separation. So I'll give another example. And that is the G versus X curve. So I'll just show there, and I'll share this codes. So sorry. So this is the G versus X curve. Now I'll give you the problem. The problem is here. So the problem that I have is here. So I have, say for example, I am trying to construct one of these lens curves, or I am just looking at the behavior, okay, at different temperatures of this free energies and stuff. So basically, if I want to do that, I have TMA given 800 Kelvin, I have TMB given, then I have been given the G0MA, right? That is the pure A molar free energy, that is, which is basically 800 by minus 10 T. Why minus 10 T? So I assume that it is 800 minus 10 T. So basically that means this is basically 800 or 8000. So this is not 800, this is 8000. Sorry, this one is to 8000. So that's what I have written here. And TMA is 800, so this is 8000, and this 12,000 minus 10 T. So basically, and as you can see here, you have this the DMA, and so this one contains the H part and this one contains the S part, right? So this is all there, as you can see here. But these are for pure A and pure B. Now I told that omega L is minus 20,000, okay, joules, and omega S I have taken as 0. Now I am telling that this is my equation. Gm equals to Xa, Gm is 0, right? Why Xb, Gmb 0 is not there? So Xa, Gm is 0 plus RT, XL and Xa plus XBL and XB plus omega S, Xa, XB. So that is the model. So I am giving you, this is the model, right? Gm solid is this and Gm liquid is this. So these are this is basically we are telling that here it will be only Xa, Gm is 0. In this case, when I am looking at solid, and here it will be Xa, GMB0, right? Xa, GMB0. Now, if I see that, this is for the liquid, because the liquid will have, so we'll see that, okay? So, what does that mean? It basically gives you this is the line. So this is at some temperature of 1000 degrees. Okay, this is at some temperature of 1000 degrees. I can also do it at the temperature of say 1200 degree. I can see which is more stable. Now, if you look at that, if you do it at 1200 degree, so you have the first curve. Basically, if I just see the liquid curve, let us look at the liquid curve only. So this is the blue curve is a liquid curve. No, the orange curve is the liquid curve. The orange curve is a liquid curve, and the solid curve is the blue curve. Because if I just hide this guy, so you see, as you can see, this is the solid curve, okay, which has a value of minus. So you have this value, right? So you have a point. So you have a minimum. However, it is not the minimum that I am looking at. What I am looking at is the tangent construction. So if I do this, you can immediately see the coexistence. So you have a coexistence here. So right, you have a coexistence here. If you can look at my cursor, then you can understand that if I draw a common tangent, okay, so that is the idea. So if I do that, so I can do the tangent also. So I have this for different temperatures. Then I create this. Derivative and the tangent line equation, you can look at that. If I do that, then at say some temperature, it's not defined. I don't see this. Acha, tangent has f x0 ab. tangent has f, the GML basically has x of t. Hmm. And I can make it a little bit of clean thing. So if you look at this, you have this term and this term. Now you have this small guy here. Oops, this guy here, and this is the derivative, and this is your tangent, and then this becomes uh, GML. Only effects. I'll just look at it. But what I can tell you is that this one, I don't know what has happened here, because I looked at XB. So this is for a different temperature, and then I just did it for now this is the derivative equation, this is the tangent equation. Mm, we will check this. I'll get back to you. So I'll get back to you with this particular error. But what I am trying to say is that for different temperatures, so basically I have done it for 1200, I can do it for 1000, and I can do it for different other temperatures. But what I am trying to say, if you draw the common tangent here, you can basically get the equilibrium values, right? You can get the equilibrium values, right? So this is exactly what I am telling. So again, you are plotting it at different temperatures and you are able to get it, right? You are able to get it, and see, this is the GML value. And yeah, so I will share this with you. I'll just fix this part with the tangent line code. I don't know why suddenly this problem is happening. Okay, so I'll fix this part, and then it is telling name x is not defined, but that is something that looks very weird to me, because the x is definitely defined. So it's x is already defined here. X is nothing but xb. So am I doing the xb correctly? Am I passing the xb correctly? This is what we have to see. So xb, and this is like 0.8 and 0.6. So this is all fine. And it tells me y equal to fx. Okay, so I'll get back to you, and I'll share this thing. Okay, so in the next lecture I will go into the chemical reactions. Okay, so basically what I wanted to tell, so this part unfortunately this has some small problem here. We will fix this. Okay, so what I want to tell here is that if you do the delta GA bar, so basically as I am telling you that once you know these values, you can get the, from the tangent, common tangent, you can get the intercepts, right? You can basically get the mu A. So here I have anyway calculated them. I just want to show you numerically, mu A and mu B. Okay, so you have got it here. So you get these values, and you have the delta GA bar and the delta GB bar, and you can basically get the activities, right? You can get the activities. So if you look at this, RT ln AA comes out to be this, omega xb squared plus RT ln XA, and this basically, that means RT ln gamma XA is this one. So RT ln gamma A, see this and this cancels out. So you have RT ln gamma equals to omega xb squared, or ln gamma equals to omega xb squared by RT, and you get the gamma A value. So what is gamma A at the critical temperature? If I tell you, so at the critical temperature, you just put the T equal to, what is that, at T equal to Tc is nothing but omega by 2R. So here you have to put omega by 2R, and then if you want to find that critical temperature, again at critical temperature at the critical point, then basically we are also looking at x equal to 0.5, right? So now in the next part I will start with the reacting systems. Okay, so I will start with the reacting systems. I am ending it here now, and I am stopping the lecture.